Welcome to Barry's In the Interim podcast, where we explore the cutting edge of innovative clinical trial design for the pharmaceutical and medical industries, and so much more. Let's dive in.
Well, welcome back, everyone, to In the Interim. I'm your host, Scott Barry. So welcome back. For those of you who have joined multiple times, I hope you still have enough alpha to keep joining us here in the interim. I, of course, make jokes, but that is related to today's topic. So I'm going solo today. By the way, I've had people, if you can see the video of me, you can see in my background, I have this beautiful view of trees. It looks like I'm in a tree house. I'm actually at my cabin. So we have a cabin near Brainerd, Minnesota. So I grew up in Minnesota, and many people in Minnesota have their little cabin on a lake somewhere. And we spend about 3 months, somewhere 3 to 4 months up here in Minnesota. We get out of the heat of Austin, Texas in the summer. We get to enjoy this beautiful Minnesota summer without having the Minnesota winter or the Austin summer. We kind of get the best of both. We are approaching the time at the end of the year that we travel back to Austin. It'll be in a couple weeks we travel back to Austin, so you won't see this view of my treehouse. I'm essentially in a little room above the garage here in the cabin, where I do my work and the podcast, and we have this beautiful, beautiful set of trees out the window. It's gorgeous. We're about to embark on this trip back from Minnesota to Austin, and we have a big dog, a Bernese Mountain Dog Poodle mix, a Bernie Doodle. He's about 110 pounds. So, of course, we drive back and forth each way. So we drive up here, we drive back. I've even started to, 2 days is just kind of brutal. It's about 20 hours, 19 hours total. So I've started to try to do that in 1 day. My wife won't do it with me, but the dog and I jump in the car and we leave at 4 and we get in, 10, 11 o'clock at night. I think we're headed back. I think we're going to do it 2 days. But I want to sort of set up that when we do this, there's multiple cities that we drive through. So we're a couple hours from Minneapolis. There's multiple ways in and around Minneapolis. And the traffic in Minneapolis, St. Paul has been challenging. It's construction season, as every summer is here in Minnesota. We drive through Des Moines. That's usually not too bad. But Kansas City has multiple routes around it that you can take depending on the traffic. Same with Oklahoma City, and the biggest hurdle is Dallas-Fort Worth, depending on the timing we go through it. And there are many ways in and around Dallas-Fort Worth, depending on the traffic. So we get ready to drive out, and we're thinking there's multiple routes we can go. And of course, we're aided by our maps, and we can get updated views of traffic and how long each one's going to go. So do I decide on how I'm going to get around Minneapolis when I drive out of our cabin here in Brainerd? I'm still, 2 hours plus away. Do I decide how I'm going around Dallas-Fort Worth when I go through Oklahoma City, where I'm still a couple hours away? It seems like that would be absolutely nuts to make that decision, especially when I have an app that gives me the most current view of traffic. I'm going to make that decision when I need to make that decision, as close as I can to making that decision. And it's going to provide me the most efficient way home, which for me is the shortest route in that. And forcing myself to make that decision 2 hours earlier or, 5 hours earlier seems to be bizarre. Okay, so let's jump in today's topic. And today's topic is the promising zone design. It is, here at Barry Consultants, we're in the interim. We do adaptive designs. It's really our expertise. I've been doing this for 25 years, and the promising zone is an adaptive design. It's an adaptive sample size approach. So let's talk about the promising zone. It's actually a beautiful, neat mathematical result. The question is, that mathematical result tied to a design, is it good? Does it work well? So let's get into that. And one of the challenges, and it's sort of fun in doing this podcast, is I can't use slides. Now, I think there's probably a functionality where I can put slides out there and all that, but you don't want slides and all of that. So some of you are out for a jog, some of you are driving to work in the morning. You're consuming this in different ways. And so I sort of have to describe this to you. So I'm going to walk through a little bit of this with no slides, which is a challenge, but I think is a good challenge, actually. And something to think about when you give a talk at a conference is, can you do that presentation where slides are an aid to you, but not a crutch? So I'll try to do that. I may fail. So the simplest of designs, where this is adaptive sample size, we're running a phase 3 trial. We have a standard one-sided 0.025. And, I've said this on multiple podcasts, but a two-sided superiority trial is just strange in this. So we'll continue to talk about one-sided alpha of 0.025. Now, I'm going to set this up within the context of a test of a mean. So at the end of the day, we're doing a t-test in ANCOVA, an MMRM, where we're doing a test of means, and a higher mean is good. We'll think of a standard deviation of 12, just so I can have a range of effect sizes. And in this scenario, let's sort of identify that a mean change of 4 points on this endpoint is really where I'm targeting. I think in my phase 2 trials that we might be as good as 5. We may even be north of that. But I really want to make sure I'm powered for 4. 3 is clinically reasonable in this setting. If I can do 3, that's a marketable drug that's going to help patients. I think it's approvable, but it's a big trial. If I have to power 3, it's a bigger trial. And so that's where I'm stuck with. And a lot of companies are stuck with this sort of exact scenario. I might be 5. I might be standing on a drug that has a mean change of 5 in my population enrolling. So 1-to-1 trial, straightforward. So in that, a fairly standard thing is I can think of, okay, that effect size of 4 to be powered for 4 with a standard deviation of 12, 1-to-1 randomized, I'm slightly over 80% powered if I do 300 patients, 150 and 150, slightly over 80% powered. Very standard decision that a sponsor can make to run a fixed sample size 300 patient trial. Now, the question is, can we do better than that with an adaptive sample size? If we did a 500 patient trial, I'd be 80% powered for the effect of 3, that slightly smaller effect if I run 500. But I don't want to run a 500 patient trial because I think I'm north of that. But if it's 3, yes, I wish I would have run a 500 patient trial. Now, I could run a 200 patient trial and I'd be about 84% powered for an effect size of 5. So I could run a trial anywhere in there, 200, 300, 500. So can we do an adaptive sample size? And maybe this is the perfect scenario for a promising zone design. And we'll come back to sort of different ways to view this, but what is the promising zone design? This was aptly named, and we'll come back to the name promising zone design. It's a beautiful name, but it's a beautiful mathematical result as well. So Mehta and Pocock, 2010 article in Statistics in Medicine, named the design that uses this. And the beautiful, clever mathematical trick here is they have a way in which they don't spend alpha. And it's a really neat, it's a powerful result to think about in adaptive designs. So what is the result? The result is, and I want you to envision a sort of 2x2 table, and it exemplifies that looking at data doesn't cause alpha. It's the actions you take depending on the data that can trigger the need to adjust alpha. And that sort of 2x2 table is on the columns here is that the data are good or the data are bad. And I'll come back to what exactly that means. But think about good data at an interim and bad data at an interim. And then the different sort of actions you can take are making the trial smaller and making the trial bigger. So that's my 2x2 matrix I'm looking at here. When the data are bad and you make the trial smaller, usually that's futility. So I do an interim and the data are bad. I'll come back to bad and good, and that's the sort of clever trick of the promising zone design. Is when the data are bad and I make the trial smaller, I typically stop for futility. You lower the overall probability of a type 1 error in the trial because largely you can't win that trial in that scenario. So things that lessen the sample size in that case are going to deflate type 1 error. Nothing you do in that realm inflates type 1 error. Looking at the data and doing futility decreases type 1 error. Now, if you make the trial smaller when data are good, this is really sort of group sequential. If the data are strong enough and we stop the trial, what people refer to as early, and I think the terminology is you declare superiority, that's the opposite sort of action you take when the data are good, making it smaller. That can trigger inflating type 1 error without adjustment. So when we're going to do that, we're going to make it smaller. When the data are good, we adjust alpha. So that's making a trial smaller. In some cases, you don't inflate type 1 error. In some cases, you do inflate type 1 error. When I make a trial bigger, that's somewhat the opposite of that group sequential type triggering, calling superiority or futility. So suppose the data are good. Let's do the other one. Suppose the data are bad and I make the trial bigger. That actually inflates type 1 error. And it's the circumstance if I was originally planning a trial of 300 and my data are bad, and I say, let's go to 500. That is something where you're taking a bigger sample size because the data are bad. You're trying to wash out the negative data you have now with a bigger sample size. That inflates type 1 error. Now, when the data are good and I make the trial bigger, you do not inflate type 1 error. Now, one of the actions that fall into this bucket is response adaptive randomization. When you have multiple arms in a trial and you increase the randomization to an arm that's doing better, you have an effective sample size that's bigger. When data are good, you're giving it, we want more data on that arm, you actually decrease type 1 error. Now that's a multi-arm trial scenario here. And in this case, that's not a 2-arm trial, that's a multiple arm scenario. But the other part where this happens, where the data are good and you make the trial bigger, is the promising zone. Now that's the neat little trick about the promising zone is when the data are good and you make the trial bigger, you don't need to adjust alpha. Now, I said, what does good and bad mean? It's a neat result where suppose I'm going after a trial that's 300 patients and I look at the data at 200. What does good and bad mean? Largely, if I am trending to a successful trial at 300, meaning my conditional power is above 0.5, that if I do exactly where I am or a little bit better, so my effect size is what I need to win or bigger, and I increase the sample size, there's no need to adjust alpha. Because I'm in this realm of my data are good and I make the trial bigger. It's kind of the opposite of group sequential. When the data are good, you make the trial smaller, it needs adjustment. So that line of good and bad is a 50% conditional power. Now, you can lower that a little bit. And the paper talks a lot about defining good and bad depending on when you look and when the 300 is. So they give an example where they can do a cutoff at 37%, and that defines good and bad, and no adjustment to alpha is needed. As long as we're 0.37 or better, we could increase 300 to 500, and you don't adjust alpha. So really neat sort of summary of adaptive designs and spend of alpha. It's a really neat mathematical result. So what they do is they pack that into a design, and they call it the promising zone design. Now, I'm going to simplify it a little bit, but they talk, the general concept of this design is, okay, I'm originally targeting 300, and I have 0.025 at 300. Remember, that gave us 80% power for an effect size of 4 that we're targeting. Now, in order to use this result, I have to go backwards in time to an earlier time. I can't use this at 300 because at 300, my conditional power at 300 is either 1 or 0. So I have to do my look for adjusting sample size earlier, like 200, so that I can use this neat mathematical trick. So I go back and I do an interim at 200. Yes, you can do a superiority analysis at that point, say, and they do talk about spending 0.001 alpha for superiority there. That's your choice to do that. But at 200, I look to see if my conditional power is above 0.5, and let's say we can calculate exactly the threshold in the integral, and it's 0.4. So 0.4 or above, I can increase my sample size from 300 to anything I want, to 350, to 400, 500, without adjusting alpha. So let's say we can adjust it to 500. They talk about the case that the data at that time point triggers exactly what your sample size is between 300 and 500. Turns out it very rarely picks a sample size between there. It almost always goes to the biggest you'll allow it to do. It also can be unblinding if the sample size is 340. You know exactly what the effect size was because of the conditional power. So let's simplify it in this case to be that if the conditional power is above 0.4, we can increase the sample size to 500. And our analysis at 500 uses 0.025. So we do this spend-free. The crux of it is the mathematical trick tells me when I can increase my sample size, and it's this 0.4 or above. And the design usually does something like from 0.4 to 0.9 in conditional power, I'm going to increase the sample size to 500. But if it's above 0.9, I'm really liking my chances of winning at 300. I'm going to go with 300. I'm not going to increase it because my conditional power is high. This neat mathematical trick allows me to do this without any alpha spent. So the promising zone design is do an interim at 200. If my p-value at that time's significant at 0.001, I call significant, my trial's over. If my conditional power is above 0.9, but I haven't won yet, I'm going to stick with 300. If my conditional power is between 0.4 and 0.9, I'm going to increase from 300 to 500, giving me that additional power. Now, if my conditional power is less than 0.4, I can't increase. That was this other place where my data are bad. Bad is a bad term. For that, where it just largely means my conditional power is in this region where if I want to increase sample size, I need to adjust alpha. And that's sort of, we're not doing that in the promising zone design. There's this, well, I'm going to say, I think it's a bad approach, but we don't want to spend alpha, which I think is not good design. Your role is not to preserve your alpha. Your role is to create a good design. But that's the premise of this design, and it's why it's attractive to people, is you don't actually spend alpha. So if it's 0.4 or lower, I have to stick with my 300, knowing that my chances of success are reasonably small. And boy, if my conditional power was 0.3, that's the case where I would love to increase to 500. But the mathematical trick doesn't allow me to do it. This mathematical trick is making my drug development decisions. And me personally, it makes me uncomfortable in that scenario. But how does this work? How does this design work? So that's the design that I described. You could embed futility in there, and I'll leave that aside for now. I think that's a very good idea within the scenario. So in this design, when you employ that design, let's think about what happens in the trial. At 200, you do this interim. Largely, if your effect size is sort of north of about 5.5, remember, if it's 4 has a power of 80% at that 300. But if I'm north of about 5.5, I'm going to win with the group sequential 0.001. Oh, by the way, I said 0.025 alpha. Because of that 0.001, it's 0.0249 in that case. But largely, it's 0.025 in that setting. So if I get to 200 and my effect size is above 5.5, largely I've already won the trial and it's over. Now, if it's in that region of about 5.5 down to about 4, in that case, I'm trending with 90% conditional power and above. I'm going to stick with 300 in that case. So my conditional power of 0.9 is about effect size of 4 in that case, which is originally powering 4. So if I end up north of that, I'm really trending to a successful trial. Remember, 200 patients into my trial, I have a mean in the bank of 4 or above, gives me a conditional power with only 100 patients to go that I'm going to win the trial. And remember, I'm powering at 5 at 300. If I see something north of 3, I'm going to win the trial at 300. Okay, now the promising zone is labeled as that region where I'm between 0.4 and 0.9 in conditional power. When it falls in that case, those are effect sizes just below this, I need 3 to win sort of thing. And it's about 2.7 or above where I'm going to have 40% chance of winning at 300. 2.75, let's call it. So 2.75 up to 4 is the defined promising zone. That's the case where I'm free to increase to 500. So I'm going to go to 500 in that case. If my effect is 2.7 or less, I have to stay at 300. So I'm going to go to 300 in the trial. That's what the design does. That's what it looks like in the effect size of this. Now, what are the ramifications of this? First of all, I want you to think about trials that go forward into the promising zone, have conditional power at 300 to win between 0.4 and 0.9. Most of those trials would have won at 300. More than 50% would have won at 300. So when you go to the promising zone and you go to 500, it's going to increase that. So you simulate exactly that design. Remember our old case of 4 that had power of about 82%. That goes up about 4%. In the case of 4, we increase our power by about 4%. We also, I'll sort of stop there. Our sample size, our average sample size increases from 300 in the fixed sample size to 342. That's not a sort of small increase, but if you ran a trial of 342 patients, you would get the same 4-ish% increase, 4 to 5 increase in power. Is that efficient? No, it's not very efficient. Yes, it's better than the fixed design in power, but not really in efficiency. It's a marginal benefit in the case of 4. Now you're 80% powered, and now you're increasing that 4 or 5%. So I'm not going to say that's bad in that. What about that case of 3? 3 was the case that we were lingering just below 60% power, and 500 was going to give us, in that case, it was going to give us 80% power if we ran 500. The power in that case increases about 6%. And our sample size increases by 55 on average, 355. We also increase there's about a 2% chance that you lose the trial at 500 that you would have won at 300. That can happen. If you just would have gone to 300, you would have won, but because you went to the end, it actually ended up getting worse. So you get this sort of plus 5%, but you lose kind of 2%. I'm sorry, plus 6%, but you lose 2% that you would have won at 300, and you spend 55 patients for that. Again, 355 patient trial has more power than the promising zone design on average. If you as a company run this promising zone over and over, you're not efficient with the use of your patients. Okay, so and this is sort of a perfect case of the promising zone. Is it better than a fixed trial? I don't know. I'm not so sure in that case. But let's the attraction to it is sort of this bizarre allergic reaction to spending alpha. Again, the goal of the trial is not to preserve your alpha. So many companies come to us and say, oh, we're doing a promising zone design. Oh, because we don't want to spend alpha. Well, it doesn't mean it's a good design. It doesn't mean it's efficient. Have you compared it to other designs? Let's take exactly that trial and say, under those parameters, let's do a group sequential design. Let's spend alpha. Now, I should stop saying spend, because spend sort of means like it's gone. You allocate it across this. You still get 2.5% alpha. You haven't lost any of it. It's all there in the design. You just use it at different points in the design, hopefully in an efficient way. We're going to use a fairly non-controversial Kim DeMetz 2 spending function. And we'll use exactly the 200 case that the promising zone did. And then we'll do 300. That was original sample size. We'll allow 400 and 500. So here's a design that has the exact same range, the same minimum, the same maximum, and we use a Kim DeMetz spending function over those. By the way, the final alpha at 500 is 0.0173. And again, that gets people so nervous that that's less than 0.025. And that's what they call the spend. Yeah, but it's all used. You use all of that alpha at 200, 300, 400. It's so strange to me that people have this allergic to reaction to using their alpha in efficient ways. So what does that design do compared to the promising zone design? Fairly simple. Straightforward, right? I haven't even baked in futility. At 400, at the effect of 4, remember we were a little over 80% powered for 300 patients. The promising zone increased that, let's call it 5%, for an average of almost 50 patients more. The group sequential design at 4 has a power of 95%. It goes from about 82 to 95%. More than double the increase in power at 300 at the effect size, our original goal of 4. The average sample size is 310. The promising zone average sample size in that case was 342. No different than a fixed sample size of 342. The power of 310 patients at that case would be about 83%. Ours is 95%. That's an efficient use of your sample size. If you're running 5 of these trials, 10 of these trials, If the industry's running many of these trials, it's an incredibly efficient use of the sample size, patience, time, cost in that. It's much better than the promising zone design. And it allocates alpha across these. Remember that little 3, the effective 3, that boy, we'd love to go to 500 in that circumstance. The power increase in that case is more than 20% increase in power. It almost gets to that 80% that we get. It's about 78%. It's almost a 20% increase in power. The promising zone increased 5%. And the promising zone increased it by 55 patients. This increases it to 383, but you get a huge increase in power. You almost get the power of a 500 patient trial for an increase of 83. Again, incredibly efficient use of alpha. Same thing happens for an effect size even of 2 in that circumstance. Of course, the other beautiful thing is if your effect size is 5, your power is almost 100% and your average sample size is 250. Because you win at the 200 patient look 60% of the time. Again, it's incredibly efficient use. The group sequential design dominates the promising zone design. I don't care if you spent alpha, it just doesn't matter. When you simulate and compare that design to the promising zone, there's no way you'd pick the promising zone. Okay. Now, embedding within that, people get nervous, well, you might go to 500. You need to embed futility within that. Add futility rules at the 200, 300, 400, 500, simulate it, optimize it in those scenarios, create a much more efficient design. The amazing thing about the group sequential design, and by the way, I'm a card-carrying Bayesian, but I live in the world of type 1 error in phase 3. And I did that discussion with Frank Harrell. He gets mad at us for doing this, but it's the world we live in. And we do group sequential designs. We explore designs and look at the optimal. So I'm not somebody standing up here saying frequentist is great and all that, but the design is pretty darn efficient in the world where you have to control type 1 error. It's really darn efficient in those circumstances within that. So the group sequential design can be incredibly efficient use of it, tied with futility, tied with simulation, compare it in those cases. We get so many clients coming in that don't want to spend the alpha, and they write in a promising zone, and it seems like this amazing thing. Oh, sorry, what I was going to say, when you do this group sequential design at 200, where again, you win north of 5, you stop for futility based on some point where you decide as the sponsor where that is. You don't use the mathematical trick to say it's 0.4. You decide at what values you would like to keep going in those circumstances. It creates a promising zone between your futility and we won. That's the region we'd like to keep going. And then at 300, it creates another one, another promising zone. The difference in the designs is you make the decision of whether 300 is the right sample size when you get to 300. You don't have this weird mathematical trick say, we need to go back to 200 to decide if 300 is the right sample size, because there's this cool mathematical trick about good and bad data and spending alpha. The promising zone's been out there, and it's a siren song for people. Oh my God, there's this adaptive sample size approach that doesn't spend alpha. It's a siren song for people. Simulate the design. Compare it to a fixed design. Compare it to a group sequential design that allocates alpha. We at Berry have never once had a scenario where a sponsor comes in where the promising zone design is better than a group sequential design. 0. If you have one out there, show it to me. I'd love to see it. I'd love to see this rare bird out there. Now, Interestingly, of course, in the whole thing, and it's more than I can do in this episode, but that was a circumstance where you had complete information on every patient. Now, most trials don't have that. Our endpoint is 12 months. Our endpoint is 6 months. Our endpoint is 90-day modified Rankin. A number of scenarios that when we do our interim, we have a number of patients with incomplete information. You can do group sequential designs with incomplete information. Now, we call those Goldilocks designs, and you can look up Broly, O'Connor, and Berry paper on Goldilocks design, where largely you're employing group sequential techniques. When you get to 300, you make the decision is 300 right. You don't know the final answer yet. You don't know your p-value. You can use conditional power or predictive power to say my probability is high, I'm going to win right here. And then I stop enrolling, I get complete data, and I do my p-value calculation. With incomplete data, that's still better than the promising zone, because remember, the promising zone goes back to 200 and says, I now need to forecast 300, but it has incomplete information. Because at 200, it is also dealing with the same problem. In all of those same circumstances, the promising zone has never been better than a Goldilocks group sequential type design. Now, it's one of these circumstances that math triggers the design, and that just makes me incredibly uncomfortable. This neat mathematical result that you don't inflate type 1 error at 0.37 or 0.4 or 0.43 should not be your drug development decision. Don't force a decision earlier to do this neat little mathematical trick. Don't make your decision about where you're going to go around Minneapolis 2 hours earlier. Now, it's not all that different of a scenario because we have incomplete information. So when I get to the top part of Minneapolis, I have to decide 494 to the west. I can go 94 through the city. I can go a little bit east of that. Now I have incomplete information when I get there. So right about the point I have to make this decision, the app is going to tell me the relative time for each of these and some rush hour time. And I think pretty bad in Minneapolis in that. So I'm still dealing with incomplete information, but I'd rather do it close to the time I have to make the decision rather than when I leave my house 2 hours earlier. It can't be possible that I can make better decision 2 hours earlier. And in this adaptive sample size thing, that's what is done in the promising zone design. Sure, it's better than a fixed sample size. But once you get into this world and say, I'm in a scenario where I could go to 500. If the promising zone says go to 500, I could have a flexible sample size. Do it right. Simulate it. Explore the different approaches. Don't just write in the promising zone. It's, in the siren song, they run into the rocks, and it's not good. Compare it. If you find a case where the promising zone does better, let me know. That's really cool. But we have yet to find that one. Make the decision when you need to. Don't make it earlier than that. And be efficient with your use of alpha. Here in the interim, we take that seriously and we try to use our alpha efficiently. We also try to drive and get there in the shortest amount of time. And I'm heading there. In a couple of weeks, we'll be making that trip in there, and I plan to have my app open, telling me which way to go and not making those decisions before I get to that point in the road. So I thank you all again for joining me here in the interim. Until our next interim, cheers.